Hello everyone. So this is now a problem in solving for heat of reaction. The data that was used for this problem was obtained or were obtained from an actual experiment entitled heat of combustion. In that experiment, there were two major steps. The first step was to mix hydrochloric acid with magnesium oxide powder, and the other step was to get another reaction by mixing hydrochloric acid and raw magnesium. So for both steps, for both reactions, 100 ml of hydrochloric acid, of 1 molar hydrochloric acid was used, and for the amount of the solid, we used 1 gram of magnesium oxide and half a gram or 0.5 grams of raw magnesium. And then for getting the initial temperature, this one was obtained by getting the temperature of hydrochloric acid before mixing the magnesium oxide or the raw magnesium. So for the first reaction, the initial temperature I obtained was 28 degrees Celsius. And for the second reaction, it is very close. I obtained 29 degrees Celsius. To get P2, what I did was, of course, mix and stir the solution. And after it settled around a minute or so, I got 34 degrees. This was the time wherein it was not increasing anymore for the first reaction. And I got 48 degrees Celsius for the second reaction. So this data will be used in solving for the heat of reaction. So let's just get delta T. So delta T here is 34 minus 28, that's 63 Celsius. And here, that's 48 minus 29, that's around 19 degrees Celsius. Okay. This would be the only data that we'll be using to be able to solve. Okay, so for the chemical reactions, these are already given in the problem. So our target reaction is actually this one, magnesium plus 1/2 oxygen yields magnesium oxide. So we are also given the step reactions. So for the step reactions, we have three. We have this one, and then we have the one for magnesium. And we also have one with water and oxygen. Sorry, not water. Hydrogen and oxygen together. That yields a byproduct of water. And given for the third reaction, which is the catalyst, we're given already the enthalpy or the heat of enthalpy. It's negative 285.8. The negative sign, remember, for the negative sign always indicates that this is an exothermic reaction, meaning it is releasing heat. So for the constants, we'll be using the following. For specific heat, for this problem, I'll be using 4.184. Molar mass of MgO, 40.3. And then for molar mass of magnesium, that's 24.3. So if you might be wondering how I got 40.3, so that's MgO. So just go over your periodic table. So we're looking for Mg. So Mg is 24.305. Okay, I'm sorry, I'll go back to that. So the conclusion is 24.305. So that's 24.305. And for oxygen, we go back to our periodic table. We look for oxygen, it's 15.999. I usually you round that up to 16, but let's go to 999. So that's 4, so that's 5. So that's 3, sorry. And then that is 0, that's 4. That's why it's 40.304. Okay? So that's coming from there. And then 24.3 because at the onset it was already 24.3. So given all this information, we'll be able to solve for the target heat of reaction. So the next step would be, if we knowing that data, we'll be solving for the heat quantities for each reaction. So for Q1, or for reaction 1, which is, in our case, the magnesium oxide. Okay, so I'll just wait for this to change frames. Wait for reaction 1, which is for magnesium oxide. We will be solving for heat, so that's Q equals mc delta T. So the mass should be inclusive of the hydrochloric acid and, of course, the magnesium oxide powder. So that is 100. So if we go back to our original data, that will be 100 grams plus 1 gram. So this is 101 grams. For our total mass for the action 2, that's 100 plus zero point 0.5. Therefore, this was 100.5 grams. So we go back to our computation. So we'll be using mass as 100. Oops, sorry. That's 101. And then our C, we'll be using the C of water. So that's 4.184. And then delta T, we've already computed that. On the initial table, that will be 6 degrees. So let's just get my calculator here. So it's 101 times 4.184 times 6. That will be 2535.504, and that will be in joules. So that is our Q for the first reaction. Let's just sign that as Q1. Now, for getting the heat of reaction, we can already solve for delta H, and our delta H will be, of course, Q1 all over the moles of the limiting reactant, which is magnesium oxide. Okay, our limiting reactant for this one is magnesium oxide. Okay, so we will just substitute our values. That's 2535.50. Let's just use that. All over, we will be using the molar mass. It says there it's 1 gram. Okay, we use 1 gram of magnesium oxide, and for our molar mass, we have 40.3 grams per mole. Okay, all we have to do now is, of course, compute this. Okay, I'm getting, that should just be 2535 times 40.3. I'm getting 102.160. So it's 102.160.5. If there should be differences in our, what we call this, in our decimal points, perhaps it's the C of water, or where we rounded up for the decimal place that makes the difference. By the way, let's make this negative so that we can indicate that it is exothermic. So this is now in kg per, this is now in joules per mole. I'm sorry. Okay. I'm getting 102.160.5 joules. So my delta H now should be negative 102.160 kg per mole. Okay, I will be using this, okay, later on when we will be solving uh, the heat of reaction using Hess's law. So let's just put a subscript 1 just to identify that this is for the first reaction. Now let's solve for the second reaction. So we'll do the same thing. For reaction 2, we'll still be using Q2 equals MC delta T. In this case, our M here is 100.5. Our C is still 4.184. And then our delta T is 19 degrees. So just compute Q2. So Q2 now is 100.5 times 4.184 times 19. So we're getting 7989.35 or 348 to be exact. And then this is again negative. So this is also in joules. Now we'll get now the delta H2. So our delta H would be again just copying the formula that we did. Instead of Q1, now this is Q2 all over, of course, the moles of the limiting reactant. That's quite long. And then we'll just use 7, 9. Oops, sorry. Let's just erase that. Okay. That's 7989.348 all over. But we only use half a gram of magnesium. So that's 0.5 all over the molar mass of magnesium. It's 24.3. I'm sorry, that's 24.3 grams per mole. That's, sorry for that. That's 24.3 grams per mole. This is in grams, sorry for that. Okay, and then all we have to do is again compute for the heat. So that's 7989.348 divided by zero point 0.5 and 24.3. So we're getting 388,282.313. And this is now in joules per mole. So delta H2 now in kilojoules per mole is 388.28 kg per mole. Again, have to indicate yes, this is exothermic. So after which, what do we do next? Then we have to use our Hess's law. Okay. The total heat of reaction using the step reaction. So our target, remember, we said the target reaction is this one. Okay, I can actually use this one. Let's just copy it. Hopefully I can copy it so that we don't have to like write the whole thing all over again. Hopefully just let's copy it. Oh, okay, my bad. So let's just duplicate the page. This is really live. So let me just duplicate this page. Can I actually duplicate the page? So I guess I cannot. In GoodNotes, I cannot duplicate it. I was supposed to copy the page. Let's see if it's copied. No, it's not copied. So let's just rewrite it. Okay. Or probably I could erase it and I can copy it. Okay. I guess that'll be better. Okay. So should there be questions, by the way, you can always comment on the video. Uh, I'll be much willing to give you detailed, there, that is better, detailed explanation. Perhaps you can PM me or you can message me. But for the video, hopefully this is already clear. This is the simplest way I feel that I can answer the problem. Okay, here. So this is our target reaction so that I don't have to write them all over again. And besides, oops, sorry, what's that? Oops, oh, I think that's weird. Okay. Now let's solve them. So what did we do up to this point? We got the delta H's of each step reaction. So NGO, the heat is from aluminum oxide negative 102.16. Let's just write there negative 102.16. Okay, and then for magnesium, we have negative 388.28. Okay, all of these are in kg per mole. So that being said, we can already solve it. We can use Hess's law. But first, let's see if they're already properly positioned. So NGO should be on the right side of the arrow. So here, I think for the first one, we have to do a reverse, or we have to invert the equation. So let's do that. So that will mean Mg, okay, Cl2 plus water yields what? MgO plus 2HCl. And then since we did an inversion, we can say that this is positive 102.16. And then the second one, do we need to reverse the reaction? I don't think so because we need Mg on the left side. So that's Mg plus 2HCl yields MgCl2 plus H2. And that stays at negative 388.28. Next, for the last one, do we make it stay? Yes, we just retain its position. H2 plus 1 half O2 yields water, and this is negative 285.8. If you know this, you can already solve it. So let's see. Using our Hess's law, remember for Hess's law, it's only the sum of the step reactions. And whenever you see the compound or the element on both sides of the arrow, then we can cancel them out. So let's see, I can see water being cancelled. And then let's see, what about MgCl2? Here we go. And then what else can we cancel? We have 2HCl can we cancel? And what else? H2. There you go. Now we're left with Mg plus 1 half O2 yields MgO, which is the target reaction that we're looking for. Okay, they're the same. Now doing that, you can already compute for this one. So this is 102.16 minus 388.18 minus 285.8. So this is negative 571.92 kg per mole. So this is our answer, which is of course dependent on the temperatures that we've obtained during the experiment. So this is our answer with that given data. Now, I believe in the experiment, there was a given heat of reaction expected. So you have to just first get the percentage difference. So I hope this helps you in solving for heat of reaction, and this will help you in the experiment data that you'll be producing for your final. Okay, thank you so much, and until next video.